I'm sure you remember meeting equilibria at GCSE and AS level and looked at equilibria in a qualitative way. We're now going to put some numbers and look at it in a more of a quantitative way. So, first of all, let's recap our AS knowledge. So, what do we mean by a dynamic equilibrium? It's a reversible process that can move in either direction. Many physical processes are reversible, for example, freezing and melting. Most chemical reactions are irreversible, but some can be reversed, and there's the example of our old friend, the Haber process. So, a reverse reaction will reach dynamic equilibrium if we give it sufficient time for both the forward and reverse reactions to occur at the same rate. And that's an important point. We don't have any information on rate, so it could take a very long time to reach the equilibrium position. And as I said, when we've reached equilibrium, the forward rate equals the backward rate of reaction. It can only occur in a closed system, which means that the reactants and products can't escape, which is obviously important for gases. And at that point, there's no overall change in the temperature, pressure, or concentration of any of the reactants or products. So, how do we reach dynamic equilibrium? So let's have a look at the Haber process. Initially, when we mix them together, no ammonia is present at all. Therefore, it's only the forward reaction that is actually happening to make ammonia. However, as the concentration of ammonia increases, the backward reaction rate will increase as well. And conversely, the concentration of hydrogen and nitrogen will be decreasing, and therefore the forward rate will decrease. And initially, and then finally, we get to the stage where the rate of forward reaction is the same as the backward reaction, and therefore we have reached dynamic equilibrium. So at that stage, there's no overall change in the concentration, but the reaction hasn't stopped. That's really important. It just means that at the same rate that ammonia is being produced, um, uh, ammonia is then breaking up to give hydrogen and nitrogen. It's just different molecules that are doing this. You would have met Le Chatelier's principle, really useful for predicting the change in equilibrium position. So Le Chatelier's principle states that if we have a dynamic equilibrium and we try and change the conditions, the equilibrium shifts to minimize that change. So again, let's look at the Haber process, and we're going to change the concentration of hydrogen by increasing the amount of hydrogen in the mixture. So we're going to come along and pump some hydrogen into our reaction. So the reaction will want to shift, the equilibrium will want to shift to remove that increased hydrogen, and therefore it will shift to the right, and more ammonia will be produced to reduce the amount of hydrogen present. If we change the pressure, the equilibrium will try and reduce that change. So on the left hand side we have 4 moles of gas, on the right hand side we have 2 moles of gas. Therefore, if we try to increase the pressure, the equilibrium will shift to the right, to the side of fewer number of moles, which will reduce the pressure. If we decrease the pressure, the equilibrium will shift to the left-hand side, because the more moles of gas you have, the higher the pressure. And finally, temperature. This is an exothermic reaction, which is a forward. We always quote the forward reaction for that, and that means that the reverse reaction is going to be endothermic. So, Le Chatelier again predicts if we try and change the temperature, the equilibrium will shift to minimize that change. So, therefore, if we decrease the temperature, the reaction will shift in the exothermic direction to generate heat energy. And if we increase the temperature, the reaction will shift in the endothermic direction to decrease the temperature. So, how do we expand these ideas into A2? Well, we can now introduce the equilibrium constant, which is capital K and a little c. Don't confuse this with the rate constant, which is, of course, a lowercase k. So, this allows chemists to make quantitative predictions. So, what is Kc? Well, it's the ratio of the equilibrium concentrations of the products divided by the equilibrium concentrations of the reactions, and each have been raised to the stoichiometric coefficients, which seems quite a complex definition, but is actually quite straightforward. So Kc, first of all, in for homogeneous equilibria, where everything is in the same phase, this is often everything's in the gaseous phase or everything is in the aqueous phase. Here again, we've got the Haber process. We can write Kc out. So K stands for equilibrium constant. C is stating this is in terms of concentration, and it's the products, which is ammonia, and that's squared because we have two ammonia molecules or 2 moles of ammonia on the right hand side, and that's divided by the concentration of hydrogen cubed times by the concentration of nitrogen. For heterogeneous equilibrium, we have our reactants and products in different phases. So that's an example that we have there. And we don't include in Kc the terms for any solid or liquid in that. So we have our example there, and you can see that carbon is a solid, so we exclude carbon from Kc, and we will only focus on carbon monoxide and hydrogen and H2O. And then we also have calcium carbonate, decomposing of calcium oxide and carbon dioxide. So we have two solids there, so neither are included in Kc. So Kc is equal to the concentration of CO2. So important things to note about Kc, it's always got the same value as long as we don't change the temperature. Doesn't matter the amounts of reactants or products we started with, Kc will always be the same numerical value. Doesn't matter if we affect the pressure or if we add a catalyst. Kc is only affected by a change in temperature. The larger the value of Kc, that means the higher the yield of products. And if the forward reaction is exothermic, raising the temperature will decrease the value of K because the equilibrium will move to the left in the endothermic direction to lower the temperature.